Welcome back, guys. Sorry about the delay here. I haven't been feeling too good for the last week, but I'm all better now. So let's start talking about outlines in a more technical sense. I'm going to jump into the Unity editor here so you can have some visual aids while I'm working on this. It's going to be pretty cool. All right, so let's go in. So what you're seeing here is the basic Unity editor window, and this object right here is just a standard Unity asset. It's a little pickup, little kind of coin thing. If I move the game cam around, you can see what it looks like here. Just a default material, but this isn't actually everything you see when you're rendering something in 3D. In fact, there's two other pieces of data. There is depth and normals. So first let me go and reveal depth to you. And what this is the idea of the closer something is to the camera, well, the way I'm rendering it, the closer something is to the camera, the darker the color is. So, out at infinity, which isn't really infinity, it's more like just a decent distance, the maximum distance that you would render something in 3D. That's completely white, and then right up next to the camera is black. You kind of see it makes this kind of ghostly image of the coin. And this is how far each one of these pixels is from the camera. And this data is always here. They end up using this for like shadow buffers and other kind of effects. So this is something that you just have access to. The other thing you have is normals, and this looks kind of like color vomit, and what it is if you imagine like a piece of wood, and imagine if you glued a pencil like pointing straight up on that wood. However you bent that piece of wood, the pencil would always point in a certain direction, and that's what a normal is. A normal is a direction that's perpendicular to a surface. So a normal is an x, y, and z component, and so x ends up being mapped to red, the y is mapped to, I want to say, blue, and the z is mapped to green. And that's what you get with all of, like with this normal mapping here, is you can see the direction of the normal face pointing off of each of these surfaces. And sometimes the normals are blended, so like around the edge of the coin here, the normals are blended together, and that's why you have a nice smooth gradient here. So what most edge detection algorithms use, and what even humans use to an extent, is these two pieces of data. They use normals and depth, and from there they can generate edges. So what the very naive computer algorithms will do is they'll just look for massive changes in normal or depth, and if they see either of those, that's where they put an edge. And that's what I'm going to go and show. I'll show how Unity does it first. I'm going to turn their edge detection script. And this is how it works. Like anywhere it's detected a change in depth or normal, it goes and draws a line, and you can make it more sensitive, so you can say be more sensitive to normal changes, and now you're getting these little beveled edges captured. If you can be even more sensitive, you get to a certain point where it starts getting false positives, or even like the smooth gradients are getting captured. So default values are pretty good. There is an argument for going to 2 if you want to be more detailed. The same thing with depth. You can make it more and more sensitive to depth changes. The problem you start getting into here is that the way it's checking depth is just a general change in depth from where you're facing on the screen. So real steep surfaces like this start getting just all colored and all edged out. You see it's even getting worse here. You get to a certain point where the whole thing's just going to turn black. The last value they have here is sample distance. So basically for each pixel, it checks the surrounding pixel in a certain distance. So in this case, each pixel is going to check 1.5 pixels to the upper left, and then 1.5 pixels to the lower right. And from there it goes and determines if the depth and the normals have changed enough to warrant having a line here. You kind of see the artifacts and where it's only getting little, like, capturing minor pieces of data. It looks kind of like a weird flat, like, diagonal line. That's a product, or that's a result of the direction it's capturing in. And this usually, the other effect of sample distance is that it ends up basically doubling the thickness of your line. So if you go to 0.5, this is how you get 1 pixel thick lines. And you can see the whole thing is just 1 pixel thick. If you go to 1, now you have 2 pixels thick, 1.5 is 3. Oh, 13 there for a second. And this can just keep going up, you can go to 16, 32. Eventually it's just going to become a massive black. But yeah, so 1.5 is a pretty good number. It's thick, but it's not overwhelming. You turn on anti-aliasing, you see that it can smooth out the lines, and it looks pretty good, but it still looks pretty computer generated, and that's just because everything is very uniform. They have a couple other algorithms. They have cross depth normals, and this is Similar algorithm. It does a few more samples. It does a little bit more intelligent sample checking, so you get a couple more lines here or there. Just otherwise, the results are pretty much the same. So I have a first attempt at customizing this, and this is I call this variable line width. You can see it's very similar to Unity's algorithm, and I can turn it anti-aliasing, or I can turn it off here. I already blend the lines a little bit when I'm drawing it, so it's less necessary. But what you have here is a line that can be very thick, up to, I want to say, 4 or 5 pixels, or it can be up to 1 pixel thin. And yet, especially when you anti-alias it, you get much thinner lines. This is a much more natural looking line than the other one, just because the thickness varies. It has a bit more of a human element to it. And the way it works is, if I go to this one, you can see that it this looks very much like Unity's normal edge detection algorithm, and in fact it's based off of it. And the difference being that when it detects things close to an edge, or when it's fuzzy on the results, it doesn't either just draw black or white in terms of whether there should be a line or not. It starts doing partial results. So you get these kind of gray lines, and then the second pass through here, the variable line width, that's where it goes and will condense real thin lines into 1 pixel thick lines, or if it sees enough differences, it can make the line thicker. The trick here is I'm purposefully rendering at a 1.5 sample distance here. The variable line width algorithm checks, I want to say, that's 4 pixels or even 9 pixels at a time to determine what. Yeah, it checks 9 pixels at a time, and if it has a lot of real light-colored pixels, it knows to condense that into 1 real dark line. Where if it sees heavier combinations, it knows to thicken that out, and it can actually even tell from this kind of a series of encoded data whether a line should be blended on the edge, how to do its own anti-aliasing. And it doesn't actually end up using too many pixel checks, because the line it's dealing with already is so thick. The other way to check out this encoded edge data is to imagine it as sort of a pressure map. Like if you had a pen. This is how I originally got the idea for it. If you had a pen and you were tracing these lines, the color of the line would sort of inform you of how hard to press down on the pen or the paintbrush, whatever you're using to draw it. And that's what this algorithm essentially does, is it looks at the intensity of that line and determines how thick it should make the edges from there. And this is a good first step, but there are some issues, and I'm going to move this around so you can start seeing some of them. Like when you're turning here, you start to lose the line, and if I go back to the encoded edge data, it still exists here, it's just very thin, so it's getting sort of washed out in the thickness algorithm. But the limitations here, like especially with how these algorithms and Unity's included work, is that, for example, the depth here changes not very much. And that's because you have to, going from like next to the camera out to even a reasonable distance where you'd render things, you don't have very much precision. If you're using an 8-bit value, that means you have 256 levels of depth, and you could have much more precision there that you need to represent. Unity actually uses a special algorithm to encode much more depth data, so that it goes and will use, I would say, maybe 16 or 32 bits of data, so that it has a much more high-resolution depth map. And even then, it's not perfect. Like you can see when you're up close like this, even now you don't have a lot of precision, but you can see the banding, and that means that if you can see the banding, that's just if a human eye can see it, that means that the computer has much less to check against, like much less to determine whether there's been a decent change in depth. And the same thing with normals here. If I turn this off, these surfaces are definitely different, but because their normals are facing in the same direction, the algorithm's not going to be able to detect that they're different. Like, as far as it can tell, these normals are the same, so why should it draw a line here? So the hope of these edge detection algorithms is that either edges or normals would, detecting a change in edges or normals would cause the line to appear, but that's not always going to be the case. But there are ways to fix this, and what I'm going to go over now is basically the changes I have in mind to make this algorithm really just be as perfect as possible. So the first one is that with these with any of these kind of post-processing effects, they kind of deal with the whole scene as a whole. So if I had multiple little coins around here, maybe I can make some more right now. I'll duplicate this a couple times and you can see how they interact. Pull this back here. They deal with these all at the same time, so if I turn this back on now and I go back to like this, we're not just checking lines against this object itself, we're also checking against this neighboring object right here. And maybe if I go and overlap this might have some kind of weird effect. Oh, wrong one. Never actually done this before, so I don't know what's going to happen. Kind of exciting for a video. Not too bad, we can see that it's not always making like the lines you'd expect. But because these are distinct objects, what we'd really like is we don't want to have to do depth and normal checking against these two things. It just seems silly. Like, they're clearly distinct. We always want there to be an outline. So that's one of the first adjustments I'm going to make to my algorithm, is that when you render an object, you're also rendering an identifier. And this is probably going to be just an 8-bit value. So you could have 256 unique objects on a screen. And I say objects, but this could even be inside of an object, like a person wearing a shirt. A shirt might be a separate object than their like arms or their legs. Just something that's significantly different could have a different object identifier, and that'll always give you guaranteed lines, and you can determine how thick the line should be between separate objects. I would always assume like the maximum thickness. I think that's a fair bet to make. But the other thing that happens then is because you're not worrying about having to compare all these fancy normals and depth against other objects, you can actually get rid of having to have the depth go from right next to the camera out to as far as you can render. In fact, you can custom tailor it per object. So I can instead crunch the range of depth from, the closest point right here to the furthest point on the coin. And now instead of seeing this very like faint gradient, you get something that's very starkly black right here and going to like pure shiny white in the background. And doing that will give us a much more precise depth buffer, even with be able to shrink the amount of data it has to use and still get even more precise results, which is just going to give you more accurate lines in the first place. So the other type of improvement we can make here is just taking this algorithm from a naive approach to a approach that's more accurate to how a human would do it. So, we're handling normals and depth here to come up with the outlines, but we're treating them separately. What we really need to do is work with them together. And the idea is this: all these surfaces that have the same normal, if they really are a continuous surface, their depth will change per pixel at about the same rate. So the depth change between this pixel and, like, move down just 1 pixel here, like on that one, it should be the same as going the other direction. So if you had like 3 sections here, the depth change between here and here should be the same as here and here. So what we can do is, if they're we take it in 2 steps. So first we look for outlines that are caused by normal changes, and if there isn't an outline, then we go a step further. Then we can check the change in the depth, and if the change in the depth between our 2 samples is the same, then it's a continuous surface, and we don't do an outline. And if there is, then we draw an outline instead, and that will actually allow us to get full outline coverage in this area. Go and get the. That's what will allow us to get like the outlines here that we're missing right now, besides detecting it more accurately. And I'm not doing that right now because I need to do the other improvement first to get a higher resolution depth buffer. Then this delta calculation will work out better. And I think with those, it'll be pretty close to how a human would go and draw such a object. And there is one other improvement to make, and it's not an algorithmic improvement. It is just an improvement to the assets. This is just a default Unity asset, but if you're making 3D models that are specifically designed to be converted into line drawings like this, you just have to treat the normals a little bit more accurately than you might otherwise. So any kind of continuous surface, you make sure that they all have no normal blending, or a continuous surface like this would have normal blending, and then if you want outlines, to make sure that each section has their own distinct direction. that's the basic idea here, is that all this algorithmic improvement can probably get us to like 80 or 90% accuracy, and then that last bit is just making good assets to deal with in the first place. And since we're planning on generating all of our meshes for the cartoon anyways, that's a perfectly reasonable expectation. So yeah, that's all the outline talk I have for today, and I'll see you in a week or two. Well, see how busy I get. So yeah, thanks for watching.